magnetic boundary conditions. What is called as boundary? So that means it has some interface. Two different mediums are going to have interface. Okay. So already we have important concept about electrostatic boundary conditions. Okay, so that separate lecture you can see there. So again, here we are going to see boundary condition in case of magnetostatics. Okay, so let's begin with this. So now here we have X is going to represent the magnetic field intensity and B is going to represent the magnetic flux density. So we are going to see for both magnetic field intensity as well as flux density at the boundary, how situation is going to change, how its normal component and tangential components are going to behave. So for that, we are going to take the help of the Gauss laws. So that Gauss laws for the magnetic field, already we have derived the expression earlier. So that over the closed path, B dot ds is equal to 0. So generally, what is the Gauss law? Already you are aware of that. We have total flux will be equal to the charge enclosed, that is in case of electrostatics. And we have derived this condition for magnetostatics, where integral of the flux density over the closed path is equal to 0, which is called as the Gauss law for the magnetic field. And apart from this, we have Ampere circuited laws. So by using Ampere circuited law, what we have, integral of the field intensity over the closed path is equal to the current enclosed. Okay. So finally, in case of Ampere circuit law, we have to consider the Amperian's path. So now these two equations we are going to use here to understand the boundary condition. So now here in this situation, if you try to observe the diagram carefully, so for that, here we have, this is the medium 1, okay? So upper side we are considering as the medium 1, and here we are considering that as the medium 2. Now this one is the interface. So that interface is called as the boundary. So now for the flux density, if it is going to make some angle, okay, that situation also we are going to see, as well as the normal resolution of that flux density tangential component in case of medium 1 is written as the B1T, and normal component is written as the B1N. Whereas in case of medium 2, the magnetic flux density, that is the B2, its tangential component is B2T and B2N. Here what you are saying that if this flux density is going to make the angle theta 2 with the normal in the medium 2 and theta 1 with the normal in case of medium 1. So that discussion also will have here. But in case of electrostatics, all these situations we are seeing in the different way. Whereas if you see here in case of field intensity, again here in the medium 1 we have H1 and its normal component is H1N, tangential component is H1T. Similarly, in case of medium 2, tangential component is H2T and normal component is H2N. Okay, so when medium 2 suffix we are using here 2. So this medium 1 and medium 2, how we are going to differentiate on the basis of permeability. So medium 1, we are considering that permeability is mu1. For the medium 2, we are considering permeability as the mu2. Similarly here also mu1, mu2. Now it is important thing is here that at the interface, we are considering here that, so this cross sign, when cross with circle here shows that direction of the magnetic field is inwards towards the, like it is in the paper, if you think that it is towards the punching inwards towards the paper. So now here at this interface, we are considering that K is the surface current density here, like earlier we have K ds. So here again K is here. Okay, that is we are considering that surface current here. So that's actually surface current density here. So now finally we are considering that differential part here. For that, height is taken as the del h and width is taken as the del w. And here again we have considered the path A, B, C, D, A. So now we have to move over the path A, B, C, D, A in the both sides for the flux density as well as for the field intensity. Okay, so both situation we are going to discuss one by one here. So now for the understanding purpose here, so now same situation, if you see that already we know about this. This one is the situation here in this portion here. That differential surface is considered as the del S. So your direction is the normal component is perpendicular to the surface area, and here in the bottom it will be again perpendicular. So both are in the opposite direction. One is upwards, one is the downwards. Okay. So finally, at the interface, we have B1 and del S minus B2 and del S equal to 0. And here we are assuming that this height is almost 0. Not 0, but almost 0, thanks to 0. So finally, on the basis of that, here del S will take this side. So that is going to be, so finally we'll get here B1n minus B2n equal to 0. So that can be written as B1n equal to B2n. So it shows that normal component of the flux density at the interface or at the boundary is continuous. Okay. Since it is equal both sides in medium 1 and medium 2, in both sides it is what? Equal. And we already know that B equal to mu H. It is the product of permeability and field intensity. On the basis of that, B1 and B1n can be written as mu1 H1n, and B2 n is written as mu2 H2n. So finally we are going to equate this, and you want to means we can rearrange this also. We'll have H1n divided by H2n, that is going to be equal to mu2 by mu1. So it shows that field intensity is not continuous. Okay, it is the discontinuous at the boundary. So H is going to undergo some change at the interface. So now from the right side, we have diagram for the field intensity. So here we have to move on this path. What we have considered path is A, B, C, D. Okay. So on this path, when we are going to move, so finally here charge enclosed. So that is the in case of Gauss law. By using Ampere's law, what we have integral of H dot dl. This is over the closed path equal to current enclosed. So finally, K is the current density on the surface here, and width is taken as the del W. So finally here total current is going to become K into del W, and right side we are using this H into dl. So that integral of dl you can take as the H. So finally field intensity and that measurement of the height or width are being multiplied here. So we have to take the direction, how we are going to move. Okay. So finally here, if you see that for the A to B, so this is the tangential component H1T here. So in the same direction, in which direction we are going to move, and width is what? Del W. Now, if you are moving from this part, B to C here in the medium 1, okay? So then here, normal component is opposite of that. That's why we have minus H1n. And the direction is upwards, okay? So that's why here, this is the, from the layer, from the plane, upside is positive, bottom side is the negative. So here we are moving in the opposite direction. So minus del S by 2. Again here in the medium 2, normal components is upwards. Okay, we are moving in the downwards from here to here. So finally again we have minus H2N. Okay, and here again we have del H by 2. Similarly for the C2D here, we have tangential component opposite direction S to T and del W, and here again normal components for this portion S to N into del H by 2, and in the upper portion again we are moving in the same direction H11 del H by 2. So finally from here what we have seen, so what are the terms is going to cancel? This is going to be here again now. So finally here, so finally this is the minus, okay, H1 into del H by 2. Again here we have H1 del H by 2. So these two are being cancelled. Okay. So only we have to take care of the direction of the magnetic field. If you are moving in the same direction, take positive. Opposite direction, you take the negative. And H2N components, this is also going to be cancelled. So finally we are left with K into del W equal to H1T into del W minus H2T del W. So again, this del W is going to get cancelled here. So finally what we are going to get here, K equal to H1 T minus H2T. Okay. Now if suppose K is going to become 0, so then in that case we'll get here H1T equal to H2T. So it will show that tangential component of the field intensity is what here? Continuous at the boundary. Okay. If K is 0, without that, here K equal to H1T minus H2T. That means tangential component is discontinuous. Only in case of a special case, if K will be 0, then we'll have continuity. So now this one, same thing we can write for the in case of flux density. So that flux density again we have H equal to mu naught into H, or simply in the normal medium we are writing mu H. Sorry, here this side will have B equal to mu into H. Okay. So finally on the basis of that here, this we can write K equal to H1T will be written as B equal to mu H. So H is what? B by mu. So finally B1T divided by mu1 minus B2T divided by mu2. Okay. So again what you are seeing here that in this situation again it is also discontinuous. So the general equation we can write H1 minus H2 cross this is the normal vector equal to K. So this is the unit vector which is normal to the interface, and if it is the boundary is the current free that we have discussed earlier. So if K is going to be equal to 0, so in that situation tangential is component is here continuous. Okay, but flux density tangential components are discontinuous. Now we are seeing the situation when fields make the angle theta with the normal. Like same diagram we can utilize here. So in that situation, what we have, this normal component, how we are going to write, so that we are going to utilize here. So finally, same diagram we can recall here also. So now in case of medium 1, this is the B1, okay? It is going to make the angle theta 1 in the medium 1, and this is the normal component of flux density, that is the B1N, and this is the tangential component, that is the B1T. So finally B1N, what we can write in terms of B1, so this can be written as B1 cos theta 1. Okay, and this tangential component will be written as B1 sin theta 1. So similarly, we have situation in the medium 2 also. Okay. So in that case also we are able to write. So in medium 2 we have B2 like this. This is the normal and this is the tangential. So this is going to make the angle here theta 2. So this one is our B2N and this is the B2T. Okay. So same resolution. So finally what we have seen that normal components are continuous at the interface of the magnetic boundary. So finally B1N is what? B1 cos theta 1. So similarly here B2N will be equal to B2 cos theta 2. Okay. So and if you talk about the tangential components, so the tangential components we have seen here that H1T equal to H2T when K equal to 0. Okay, so then we are able to write this one as, so the tangential component again same thing will come. Tangential components is coming in terms of sine theta. Normal component is coming in terms of cos theta. So for the tangential component again we have B1 by mu1 sine theta 1. So this is written for the magnetic field intensity. Okay. So we have already B equal to mu h. So finally h is what? B by u. So on the basis of that here written. So finally, now we are going to divide the equation 9 and 10. So finally, we have sine theta 1 by mu 1 cos theta 1 equal to sine theta 2 divided by mu 2 cos theta 2. So finally, sine by cos is what? 10. So it will be written as tan theta 1 divided by mu 1 equal to tan theta 2 divided by mu 2. Now we'll rearrange this. So we'll have tan theta 1 divided by tan theta 2 equal to mu 1 by mu 2. Okay. So this is called as law of refraction. So it is going to travel from one medium to another medium. So it is called as the law of refraction for the magnetic flux lines at the boundary with no surface current. Since we have considered here K equal to 0. So finally, what's our finding here in case of magnetic or magnetostatics boundary condition? Finally, what's our finding here that this normal component of the flux densities are continuous and tangential component of the magnetic field intensity is continuous provided K equal to 0. So K is the current density at the surface. If it will be current free at the interface, then tangential component will be equal of the field intensity. And if this flux density and the field intensity is going to make the angle theta with the normal, on the basis of that we are getting here tan theta 1 divided by tan theta 2 equal to mu 1 by mu 2. That is called as the law of refraction for the magnetic flux line, okay, at the boundary. So these are the findings from the boundary condition. This is very, very important questions, okay. So any doubt is there, write in the comments, I'll reply, okay. Like, subscribe, share with your friends. Thank you very much.